Hello dear students. So far we have discussed various important aspects of atmospheric thermodynamics, and in the last class we have seen what are the humidity variables and how do you define saturation with respect to the vapor pressure or with respect to plane surface of ice or plane surface of water, right. So one important conclusion that we should take from the last class is that at any given temperature the saturation mixing ratio is inversely proportional to the total pressure, and the total saturation mixing ratio or the amount of moisture that the air parcel can hold will always depend on the temperature, right. So this is the basic idea. So you increase the temperature, the amount of water vapor that can be held by the parcel will be more. That means by increasing the temperature you are increasing the point of saturation. So saturation is only when whatever the air parcel can hold to its maximum ability. Right. Now, in the last class itself, we have seen that we don't have to physically add moisture to be able to reach saturation. We can rather decrease the temperature and say that at the existing temperature, at the existing level of moisture itself, we achieved the saturation. So we defined what is called as a mixing ratio, and we defined what is called as a saturation mixing ratio. When these two things are equal, we call it as saturation, right. So in today's class, we will discuss several important temperatures. We will discuss what is called as equivalent potential temperature. We will discuss how the temperature varies with respect to height inside an air parcel if you take an adiabatic picture into consideration, right. So relative humidity is also a very important parameter to define the existing amount of moisture content in a given situation, right. So the relative humidity with respect to water is generally expressed as a percentage. So you must have seen in many of the weather displays or in your applications, you must have seen what is the existing humidity at a particular point and at a particular time, right. So relative humidity is always expressed as a percentage, and it is the ratio of the actual mixing ratio that is existing inside the air parcel to the saturation mixing ratio with respect to plane surface of pure water. If you take an air parcel at a particular pressure, and then within this particular pressure and a given temperature at a constant temperature, if Ws is the amount of moisture that is required to reach saturation and W is the existing amount of moisture, then the relative humidity is simply a ratio of mixing ratio to the saturation mixing ratio expressed in terms of percentage, right. So W is the mixing ratio that we have seen, right, and Ws is the saturation mixing ratio, and you write it in terms of vapor pressure. You expand W as the amount of water vapor to the amount of air, or amount of water vapor to the amount of dry air. So you will get the same expression for the relative humidity in terms of vapor pressure, existing vapor pressure, and vapor pressure at saturation. So always remember, relative humidity is always expressed as a percentage, what is existing to what should be existing for saturation. That's it, right. Another very important, let's say, temperature which is relevant for discussions on stability or discussions on atmospheric formation of clouds. So the dew is called as the dew point. So dew point is the temperature at which or to which the air must be cooled at constant pressure for it to become saturated with respect to plane surface of water, right. See here, one very important thing is while you try to understand dew point, you don't talk about adding moisture. Dew point is not about physically adding moisture and then reaching saturation. Dew point is about the fact that if you decrease the temperature, you are moving towards the saturation with the existing amount of moisture itself, right. So the dew point is the temperature to which an air parcel must be cooled at constant pressure for it to become saturated with respect to plane surface of water, right. Now very importantly, when you talk about air parcel, you should always remember that we are talking about an adiabatic picture. Adiabatic picture allows no transfer of mass through its walls, or no transfer of energy, or no addition of heat, right. That means if the air parcel is to be cooled, then how do you achieve it? I mean, where is the energy going out, right. So if the air parcel is rising in the atmosphere, if it is rising adiabatically, then what happens? The air parcel the rise of the air parcel should be at the expense of decrease in the internal energy of the air parcel, right. So, as the air parcel rises, it will decrease its pressure. So, it will lose its temperature, right, and as a result of this temperature being lost, the saturation is achieved, right. So, simply put, dew point is that temperature to which you cool the air for it to become saturated with respect to surface of pure water, or in other words, dew point is the temperature at which the saturation mixing ratio Ws with respect to plane surface of pure water becomes equal to the actual mixing ratio. Actual mixing ratio is the one which is existing as it is, right. If you want to express relative humidity in terms of dew point temperature. So, relative humidity at a temperature T and a pressure P is given as relative humidity is equals to 100 times, I mean as a percentage Ws, the saturation mixing ratio at a temperature Td and P, and saturation mixing ratio at a temperature T and pressure P, right. So, T is the existing temperature and Td is the dew point temperature, and Td is always less than T, right. So, and one more very important thing is we have seen the virtual temperature is always greater than the actual temperature, right. So, so at some point there are few more temperature parameters we may want to understand how these temperatures are more or less in comparison to the actual temperature, right. Since you are saying that dew point is that temperature you reach by decreasing, then Td should be less than the actual temperature, right. So, relative humidity is just a ratio of saturation mixing ratios, but at two different temperatures, one at a dew point temperature, two at a temperature T, right. Now, if you are not adding moisture physically, then obviously the saturation mixing ratio at the lower value of temperature will always be less than 1, I mean less than 100%, right. So, that means that relative humidity should reach 100% and can never be, ideally can never be greater than 1, right. So, the simple rule of thumb, I mean how do you connect the relative humidity and the dew point is that a simple rule of thumb for converting relative humidity to a dew point depression, I mean the difference T minus Td for moist air, which is at least a relative humidity greater than 50%, is that the dew point temperature decreases by 1 degree Celsius for every 5 degree decrease in the relative humidity, right. So, this is the difference, I mean by what magnitude you should decrease the temperature is the dew point depression, right. So, a simple rule of thumb is the dew point temperature decreases 1 degree Celsius for every 5 degrees Celsius decrease in the relative humidity. This is how the relative humidity and the dew point temperature can be connected, right. Another very important temperature is which is called as the frost point. Just like we define dew point, we can also define the frost point. So, the dew point's definition was based on pure surface of water, that is, so you are talking about a process in which vapor liquefies, or you are talking about phase between vapor and liquid, right. Frost point speaks of the phase between vapor to solid, right. So, it is the frost point is the temperature to which air must be cooled at constant pressure to saturate it with respect to plane surface of pure ice. So, this is, I mean this is very important in the sense we talk about pure ice, I mean there is a topic, again there is a separate discussion that we will have, what will happen if you have something else, if you do not have pure ice, okay. But for now what we can take it for granted is that just like we define dew point as the point of temperature to which you cool the air so that it becomes saturated with respect to plane surface of pure water, you define frost point as the temperature to which air must be cooled at constant pressure for it to become saturated with respect to plane surface of pure ice, right. So, just for recalling the facts, in our earlier discussions we have seen that the vapor pressure due to pure surface of plain ice will always be less than the vapor pressure due to pure surface of plain water. So, the point is it will take more energy to melt the ice, and then subsequently this melted ice or water becoming vapor and attaining equilibrium with the surface, right. So, obviously, the vapor pressure due to ESI. So, that is what we have seen, vapor pressure, let us say ESI will always be less than ES due to surface of water, right. So, so having said that, the saturation mixing ratios and relative humidities with respect to ice may be defined in analogous ways to their definitions with respect to liquid water. We have defined that saturation mixing ratio. So, what is saturation mixing ratio? It is the maximum amount of moisture, it represents the maximum amount of moisture content that can be available if you have air in contact with ice, no water as it is, right. So, that is how we can define all the moisture parameters, just like we did for the case of water, we can extend those for the case of ice as well. But you always remember that the saturation mixing ratios or saturation vapor pressures of with respect to ice will always be less than those with respect to pure water, right. So, let us say, so when these terms are used without quantification, they are generally referred to with respect to water. So, what it means is that when you talk about saturation mixing ratio, or let us say when you talk about mixing ratio, or when you talk about saturation mixing ratio, let us say when you talk about vapor pressure or things like this, generally we don't always say that mixing ratio with respect to pure surface of water, saturation mixing ratio with respect to pure surface of water. So, we don't say all these things, rather when we say saturation mixing ratio, it is always meant, it is always implicit that it is with respect to water, but not with respect to ice. So, what did we learn so far? We learned that what are the moisture parameters, and these moisture parameters simply define or simply quantify the existing moisture content in an air parcel, and when do you say they are saturated, and if they are saturated, is there any other way to reach saturation, things like that, right. So, one important conclusion that has emerged out of this discussion is that in order to reach saturation, you do not have to physically add moisture into the air parcel. You can simply decrease the temperature and then reach saturation, right. So, lifting condensation level is a length dimension or is a particular height which exploits this idea of decreasing the temperatures and reaching the saturation, right. So, lifting condensation level is defined as the level, as the height, or let us say as the height, actually we generally use it in atmospheric stability discussions or cloud formation discussions, right. So, the lifting condensation level is defined as the height to which an unsaturated air parcel can be lifted adiabatically before it becomes saturated with respect to plane surface of water. So, this exploits two different aspects, one of which one is, let us say you decrease the temperature, your mixing ratio becomes equal at a particular temperature to saturation mixing ratio. The second aspect that it exploits is that in the atmosphere, temperature decreases as you increase the height. So, if you want to attain saturation with the same amount of moisture, you should decrease the temperature, and decrease of temperature must be done or can be done when you rise an air parcel, right. So, that is why the lifting condensation level is the height to which you rise an unsaturated air parcel adiabatically before it becomes saturated with respect to plane surface of water. So, always remember, we will come back to this point in our discussions on cloud formation. So, there we will realize that lifting condensation level LCL is always the bottom of the cloud. So, cloud will always form with its base at the LCL. Now, LCL will depend on many important parameters, that is a different story, but lifting condensation level, or generally referred to as LCL, is always the bottom of the cloud, right. So, during the lifting, the potential temperature and mixing ratio remains constant. Why is the mixing ratio constant? Mixing ratio is constant because it is adiabatic, you are not allowing any mass transfer through the walls, right. So, mixing ratio thus remains a constant, and the potential temperature remains a constant because it is adiabatic in nature, the rise is adiabatic in nature, and the formulation of potential temperature was such that if an air parcel is rising or sinking in an adiabatic picture, what will be its temperature when it tries to reach the pressure of the sea surface, right? But generally, the saturation mixing ratio decreases until it becomes equal to W, right? So, here you are not changing W, rather you are decreasing Ws to a level such that it becomes equal to W, right. So, hence we can say that the lifting condensation level is located at the intersection of potential temperature line passing through the temperature T and pressure P of air parcel. This is just to analyze the thermodynamic diagrams of the atmosphere, right. And one more very important temperature that we also call as wet bulb temperature. What do you mean by wet bulb temperature? So, this is a specific name. I mean, this is very important in again in atmospheric stability or atmospheric thermodynamic. So, this is the name is justified by the process that you do to measure this temperature, right. So, this is wet bulb temperature. So, the wet bulb temperature is measured with a thermometer. I mean, how do you do it? Let us say the thermometer generally has a glass bulb in which there is mercury, and depending on the temperature, the mercury will expand and expand into the pipe or into the tube, where the temperature is pre-calibrated, and depending on the temperature, the expansion is calibrated, and you will read the value of temperature, right. So, the wet bulb temperature is generally measured with a thermometer. The glass bulb is covered with a moist cloth over which ambient air is drawn. Simply, you just take a thermometer, you wrap the glass bulb or you cover the glass bulb with a cloth which is wet, I mean which is soaked in water, right. Now, if it is soaked, there is moisture on it, right, there is moisture on it, and if it is a closed enclosure, the moisture on the liquid that is on the cloth will evaporate with time, right. So, if it has to evaporate, it needs some heat. So, the heat that is required to evaporate water from the moist cloth to saturate the ambient air is supplied by the air as it comes in contact with the cloth, right. So, to begin with, you keep a thermometer, there is no moisture in the environment. As the air comes close and touches or interacts, or as it passes through the cloth, it gives some heat so that the liquid evaporates, and as this process continues slowly and steadily, there is moisture buildup in the atmosphere, and it will come to a limit when the cloth, which is with water, rises its temperature, or its temperature is increased to the point that it is equal to the temperature of the environment. Then the air does not have any amount of energy that it can give to the cloth and rise its temperature, right. So, basically a thermodynamical equilibrium is achieved between the temperature of the cloth and the environment. So, when the difference between the temperatures of the bulb and the ambient air is steady and sufficient to supply the heat needed to the evaporate air, you reach an equilibrium state. So, the thermometer will then read a steady temperature which is called as the wet bulb temperature. So, you make the bulb wet by wrapping a wet cloth around it, and you allow enough amount of time so that the air is in saturation with respect to the bulb. So, there is no more transfer of energy between the environment or the atmosphere and the bulb. So, this saturation or this equilibrium temperature is generally referred to as the wet bulb temperature, right. Now, the wet bulb temperature can be closely connected with the dew point. Let us say if a raindrop falls through a layer of air that has a constant wet bulb temperature. If you have a raindrop which falls through a layer of air that has a constant wet bulb temperature, then the raindrop will eventually reach a temperature equal to the wet bulb temperature of the air. So, raindrop is falling. If the environment through which it is falling does not have moisture, it has more temperature, then due to its temperature the raindrop will evaporate slowly and steadily, giving out moisture as long as there is no difference in the temperature. When these two temperatures are equal, you call that particular temperature as the wet bulb temperature of the air. Okay, so the definition of wet bulb temperature and the dew point both involve cooling to a particular hypothetical air parcel to a particular temperature or to a particular saturation, right. So both of them are similar in a way that both of them needs the air parcel to be cooled so that it reaches saturation. That means you are decreasing the saturation mixing ratio inside the air parcel to the level of the existing mixing ratio inside the air parcel. Both of them have the same idea, right. Now, so far we have seen various values or various parameters of temperature. I mean, how is this wet bulb temperature, what is dew point temperature, what is frost point, what is relative humidity, what is virtual temperature, what is potential temperature, so on and so forth, right. Now, one very important thing is there is always a phase transition that we generally talk about. Phase transition is evaporation of, let us say, evaporation of water into vapor, right. So, or a phase transition when this vapor condenses and forms water again, or vapor crystallizes and forms ice, or water crystallizes and forms ice. So, there is always a phase transition, right. Let us say, what is the idea of latent heat? The idea of latent heat comes from the fact that if the heat is supplied to a system under certain conditions, and it may produce a change in the phase rather than change in its temperature. So, generally what happens according to the first law of thermodynamics, whenever you supply heat, you are giving energy into the system, this energy increase should always accompany a temperature change. That is the conservation of energy. So, unlike if the heat supplied to a system under certain conditions, not always, if this heat is not able to rise the temperature, but rather produces a phase transition or phase change, then it is something which is very different. I mean, then we have to talk about latent heats. So, in this case, the heat supplied increases the internal energy and this increased internal energy is associated with a change in the molecular configuration in the presence of intermolecular forces, but it is not increasing the kinetic energy of the molecules, right. So, the heat that is supplied is able to increase the internal energy, the heat that you give is able to give molecules energy to overcome the intermolecular forces, triggering what is called as a phase transition. Let us say, for example, if heat is supplied to ice at 1 atmospheric pressure and 0 degree Celsius. 0 degree Celsius is the freezing point. So, where you don't have water, rather you have ice. But if it is, I mean, the pressure is more or less, then the things are different. But if it is at standard atmospheric pressure, 1 atmospheric pressure, and if you have 0 degree Celsius and if you have water, you will have ice, right, that is it. But when you heat the ice, what happens? Generally, what happens, the temperature of the ice will remain at 0 degree Celsius as long as all the ice is melted and water is formed. So, this heat that you give is defined as the latent heat of melting, right, simple. So, the latent heat of melting is defined as the heat that has to be given to a unit mass of material to convert it from the solid to liquid phase without changing the temperature. So, you take 1 kg of ice at 0 degree Celsius and 1 atmospheric pressure. The temperature will not change as long as the ice is not melted completely. Once the ice is melted, at that particular point, the temperature of the melted water that has come out of the ice is at 0 degree Celsius. Once the ice has melted completely, then the temperature increase will change. So, whatever the heat that you have supplied so far till that point has just been able to make the phase transition between the solid and liquid possible, that is it. So, this heat is called as the latent heat. So, this is the latent heat of melting, because this heat is given to make the intermolecular forces disappear, so that the molecules become free and they behave like a fluid, right. So, this is generally called as the melting point. I mean, melting point, now that you talk about melting point, we should remember the Clausius-Clapeyron equation, which says that when you change the pressure, the melting point will change, right. But so not to complicate the things, we will say that at 1 atmospheric pressure and 0 degrees Celsius, the latent heat of melting of water is 3.34 10 to the power of 5 joules per kg. So, if you take 1 kg of ice and if you want to melt this completely without changing the temperature, or if you want to create water at 0 degrees Celsius, you should supply 3.35 10 to the power of 5 joules of energy for this phase transition. Right. So, the latent heat of freezing also has the same value in a different way. So, latent heat of freezing has the same value as the latent heat of melting, but the heat here is not given, is rather released. Heat is released as a result of the change of phase from liquid to solid, right. So, some more facts about latent heat. So, the latent heat of vaporization or evaporation, LV, is the heat that has to be given to a unit mass of material to convert it from liquid to vapor phase, right. So, that means that you always remember. So, let us say LW, LM, right. LM is the latent heat of melting. Latent heat of melting is positive when, let us say this can be the other way also. Latent heat of melting is the heat given to water for melting it. If you take it the other way, if you are freezing, let us say 1 kg of water into 1 kg of ice, the heat that is released should be taken with a negative, let us say L, yeah. So, similarly, the latent heat of evaporation or vaporization. So, vaporization is creating vapor out of water. So, this phase transition from this liquid to gas phase. So, there is solid, liquid, vapor. So, water works like this, right. So, latent heat of liquid to vapor, you have to give heat. This is plus LV, let us say. And if the vapor condenses and forms liquid, then the heat is released. This is also called, this also has the same value as latent heat of evaporation or vaporization, but this should be with a negative sign indicating that heat is being given out, right. So, the latent heat of vaporization or evaporation is the heat that has to be given to a unit mass of material to convert it from the liquid to vapor phase without any change in its temperature. For water at 1 atmospheric pressure and 100 degrees Celsius, we talk about freezing at 0 degrees Celsius, 100 degrees Celsius, we talk about boiling of water, right. So, the latent heat of vaporization is 2.25 10 to the power of 6 joule per kg. The latent heat of condensation has the same value as the latent heat of vaporization, but heat is released in the phase transition from vapor to liquid. So, here it should be, so here in this phase it is plus LV and here it is minus LV, but anyhow the value is still the same, 2.25 10 to the power of 6 joule per kg is still the same. So, you take 2.1 kg of water at 100 degrees Celsius, then in order to convert this into vapor without changing the temperature, you should supply this much amount of heat. So, the melting point and boiling point will again depend on the pressure, right. So, this is some discussion about latent heats and various different values of temperatures, which will be used in our discussions ahead, right. So, we will stop here. We will continue our discussions in the next class to discuss about pseudo-adiabatic processes and how we can derive relation for the saturated adiabatic lapse rate. Okay.